Hi, welcome to the fourth part of the adders lecture. And in this lecture, we're going to focus on the carry propagate adders. And the carry propagate adders, basically, we're going to talk about adding in bit numbers. So before, what we did, we added one bit number to a one bit number, and we had the sum and the carry. So in this case, you can see that we are adding these this 4-bit number, which is the A, to another 4-bit number, which is the B. And notice here that we are doing this operation much like we have learned in digital logic. So it is a multi-bit number added to a multi-bit number. Obviously, the answer will be multi-bit, and we will call this the sum, which has 4-bit, and we have a carry out. Okay, so let's take this computation. We are assuming that we are having a carry in of a 1, right? So we add this to the first bit of A and the first bit of B. This addition happens to be a 1-bit addition because in this we're gonna add three 1-bit digits, and we will get a sum and a carry. So 1 plus 1 plus 0, we will have a sum of a 0 and a carry to the next position of a 1. So then we add this carry in to 1 plus 1 plus 0, again 0, and then I have a carry of a 1 all the way to the end, and we'll see that the answer of the sum is 0 0 0 0, and with a carry out of a 1. Let's see if we validate this. So what we are adding, actually, we're adding number, which is A here. This number is 15. I'm assuming we are doing unsigned number. We are adding this 15 to 0. So A equals 15, B equals 0, and the carry in equals 1. So we are supposed to get 16. And if we look at the result here, we see that with the carry out position, this number is 16. Okay. Now let's assume that we have the same addition problem, but now the carry in is a 0. Okay, so let's add the very first digit or bit position here. 0 plus, now this is the A, this is the B, so we add 0 to the first bit of A and to the first bit of B, and we get a sum of a 1 and a carry to the next position of a 0. Let's add 0 1 0, sum of a 1 and carry of a 0, 0 1 0, sum of a 1 and carry of a 0, 0 1 0, a sum of a 1 and a carry out of a 0, which makes sense because if we don't have a carry in here, right, the sum or the result should be 15, and this is what we are getting, 15. Now the interesting part here is that if I look at this problem from in the term of inputs and outputs, so the adder has in bit input of A, an in bit input of B, a 1-bit of carry in, and the output is a n bit of a sum. Okay, so this is the output. Okay, and a 1-bit of carry out. Okay, so this is in terms of the inputs and the outputs for our adder. So then the question comes, how can I design this adder? Let's make an observation here. In these additions, when I was adding bit position by bit position, it seems that I was adding three numbers, okay, three numbers, and generating a sum and a carry out. Well, I know that these can be done by what we studied in the previous lectures, by a full adder. The full adder has input of a 3 bits and an output of a sum and a carry. And therefore, this adder can be constructed by the following scheme. I can have this previous adder constructed by a full adder. Notice here I have a full adder here, and a full adder here, and a full adder here, and a full adder here. Now observe that the very first bit of A is added with the very first bit of B with the carry n. The output is the very first bit of sum, and C1, which is a carry, that will go to the next stage, okay, which is stage 2 or bit position 2, where I add C2 to A2 and B2 and generate the second bit of the sum, and C2. C2 becomes an input, okay, what this carry, which is generated from a stage 2, becomes an input to stage 3. C2 is added to B3 and A3, and we generate sum, and we generate carry 3. And C3 is added to B3 and A4, and we have a sum out and an S4. Well, let's take a look at the previous example, all right, and see if we can get the results of the previous example. So in the previous example, we were adding. Let me pick a different color here. Okay, we were adding when Cn equals 1, right, and the A, all of them are ones, right? Okay, and the b's are all our zeros. Okay, 0 0 0 0. Let's see if we get the previous result that we computed. Okay, so this is a full adder here, right? So a full adder with 3 inputs, 1 0 1. Obviously the sum is a 0 and the carry is a 1. So now the 1, this one is added with this 0 and with this one, and we get a sum of a 0 and a carry out of a 1, which goes to the stage 3. And this one is added with this 0, and with this one we get a sum of a 0 and a carry out of a 1, which is added to the fourth stage, where I add this one with this 0 with this one, and I get a sum of a 0 and a carry out, and a carry out of a 1. This is exactly what we predicted, or what we computed. A 0 0 0 0 and a carry out of a 1. Well, our hardware works, but this type of adder is referred to as carry repel adder. And it is carry repel because this carry really is repelled or propagates from the very early stages, from bit 1 to bit 2 to bit 3 to bit 4 to all the way to the end. So any problem with that? Well, from functional point of view, it generates the result and it is fine. But from performance point of view, there is a problem. And the problem is in this thick red line, which shows for me a delay of the results. And this delay is a big O of n, where n is number of bits, right? So if you have let's make this n uppercase here. So if you have 64-bit, right, your data, and you upgrade the data to 128 bits, yes, the delay will double. Okay, so now this, we don't like that. We don't like this linearity dependence. So this delay is really a big O of n. So let's try to find a better way to do it. Okay, but there have been some kind of attempts to improve this delay. One of them is the following. So since this is my critical delay, right? What I could do is I can I can make this path as fast as possible. And when we examined earlier one of the circuits, we found out that we are generating the C out prime very quickly. And if I can use the C out prime, instead of C out, I can save a delay of one inverter. Okay, and that's a good saving. But how can I do that? Well, we could do that because we can have A1 with B1, and I generate and C1 as inputs, and I generate the sum inverted and the carry is inverted. Okay, so how can I use the carry inverted? It turned out that if the adder is or addition function is a dual function. What do you mean by it is a self-dual function? What do we mean by self-dual function? What we mean is this is the truth table for one bit adder or full bit adder. These are the inputs. These are the outputs. The self-dual function is defined as follows. If you invert the inputs, your output will be inverted. Okay, well, let's check that. 0, 0, 0. Let's invert them. 1, 1, 1. So are the output inverted? 1, 1, yes. So if I invert the inputs, the outputs will be inverted. Let's check another pattern here. 1, 0, 1. Okay, the inversion is 0, 1, 0. And the output here is the carry out on sum is 1, 0. And if I invert the input, I invert the output becomes 0, 1. Meaning, inverting the inputs causes the output to be inverted. This is referred to as self-dual function. Okay, so how can I use this property to improve the adder performance? Well, very simple. What we will do is that we will generate inverted carry right here. Okay, and we will use the inverted carry. So if I use it, it means I saved from the delay of the carry out one inverter. Okay, because this is quicker to generate. Then what do we do here? Since I have a carry which is inverted, I'm going to use the inputs here as B2 prime and A2 prime. So now notice I have inverted inputs because the carry coming to me is inverted. So if I invert the inputs, right, and I'm using this circuit without these two inverters, right, I'm gonna generate I'm supposed to get inverted carry, but I don't have this two inverters, so I will get the inverted of the carry, so I will get C2. And here as well I will get the inversion of inverted sum, which means I'm gonna get sum 2. Okay, then I am gonna feed this C2. Notice C2 here was generated without the inverter, and the sum was generated without the inverter. Okay, now the carry 2, I'll use it with C2 with B3 and A3. Again, I'm gonna generate C3 but inverted so that I save the inverter. Okay, and I'm gonna get a sum 3 inverted, so I add an inverter to get S3, much like I got here sum 1 inverted, so I added an inverter to get S1. Now this inverted C3 will be fed here with A4 inverted and B4 inverted. And if I feed all of these to full adder, I will get the inverted output, which is S4 and C out. Okay, so what did I gain from all of this? Well, what I gained is that I saved here. Let's do a different color. I saved here in this delay one inverter for the carry, another inverter for the carry, another inverter for the carry, and another inverter for the carry. So I saved in this delay, okay, I saved 4 inverters. So let's go back to our original. So let's say for example that the delay for this adder here, the original adder, let's say it is 100 picosecond from here all the way to here. And so we come into our improved adder here. We say, okay, from here all the way to here, okay, it will be 100 picosecond minus 4 inverters. And let's say the inverter delay is 10 picoseconds, right? For example, so or 5 picoseconds, okay? So now, so this, the delay of this adder becomes 100 minus 20 equals 80 picoseconds. So this adder now is faster because I am saving 4 inverter delay, okay? But we still have this linearity. Say the problem here, the delay here, the delay is still big O of n. All right, so I still have that problem. I don't like this big O of n. Okay, so now we need to address this. And to address this, we need to examine carefully the generation of the carryout, okay, of the carry. And for that, we need to introduce the propagate and generate term. Okay, so let's use the whiteboard here a little bit. And so this is so when we are we define propagate and generate terms as follows. So suppose we are adding, so this is a 1 bit and B 1 bit. Oops, sorry. Okay, so let's 1 1 1 and B 1 0 1 0. Okay, and let's say we have a CN here. Okay, and which is a 1 here. Okay, and we are doing this addition. Now we define the term propagate, okay, of bit position as a of bit position I as AI exclusive BI. Okay, what do we mean by that? You see, and let's define the generate. Okay, you know what? Let's get this into a little closer here so that we okay, we leave ourselves some space here. Okay, so we say propagate I equals AI exclusive or BI, and generate I equals AI ANDed with BI. Okay, so in every bit position here, we would like to understand the relationship between the inputs, the inputs that is coming to the bit, which is let's say this is bit I or position I, okay, and you have here CI, sorry, minus 1, and again I'm not doing this in a clean way, so let's just redraw it again. Okay, so this is my full adder here. Okay, and in bit position I. So now what we need to do is we need to understand the relationship between these inputs, all right, which is AI, BI, and CI minus 1, a carry from the previous stage, and CI. So what's the relationship between all of this to CI? What about the sum? Well, the sum is not that critical. We see what the killer here for the delay is the carry. That's why we are so concerned about the carry. Now we can define the following relation. We can say that we can generate I, okay, we can generate Ci if uh, if AI and BI are ones, meaning GI equals AI ANDed with BI. So if GI is 1, it means I will have definitely a carry. Definitely I will have a carry. Right. So which makes sense. You see, look at this position here. Look at this position here. Okay, because I have two ones here, definitely I'm going to have a carry going to the next stage. Okay, now going to the next stage. Okay, now what about if one of them is one is so if one of of AI and BI has a value of 1. In this case, I'm going to say that I will propagate the carry, meaning whatever carry here, value of this carry, it will be moved here. So for instance, and this is the propagate is condition is detected as follows: a I exclusive or BI. One of them is 1. Which means that if I have, look at this, for instance, this example here. Let's pick a color here. Okay. Um, Look at this here. One of the AI and BI, one of the bit A, the bit for A is 1 and the bit for B is 0. So the propagate here condition equals 1. So which means that if I have a carry of a 1 here, huh, I'm gonna have a carry out of a 1. If I have a carry in of a 0, I'll have a carry in of a carry out of a 0, which means I will propagate whatever carry I receive. All right. So that's so two important conditions here: the generate and the propagate. If the propagate is 1, it means whatever I receive, I will send it. I receive Ci minus 1 equals 0. I will generate Ci as 0. I receive Ci minus 1 as 1. I will generate Ci as 1. So, but I'll propagate, I should say. Now, the generate says if you have AI and BI ones, you will generate a carry here definitely. Okay, so these are the cases that we need to understand going forward. Now, okay, now if I have a one thing here is that let's go back to the slides and okay, we probably can go to um, let's pick a new. So see if I can get a point here across before I move to the next. So now we would like to get, you know what, let's go back to the slides. They can. Okay, so we talked about the group, the propagate and generate in terms of a bit. Now we're gonna move to a something called group propagate and group generate. Group propagate and group generate, it talks about a group of bits instead of a single bit. So now notice that the Cout here, which is the output of the circuit, I am going to say that it is the generation of the carry from bit 1 to 4. But since Cn is coming from out, I'm going to assume that there is a phantom bit here, which is bit 0. So I'm going to say that the C out is the generation of the group generate. Which group? From bit 4 to bit 0. From this is bit 4 all the way to bit 0. I am going to assume that Cn is generate of bit 0. Now notice that there is no bit 0 here, but I'm assuming that this was generated from a bit called bit 0, phantom bit. Okay, and this is like generating in a group generate, but from bit 0 to bit 0. It's the same, just notation wise. Now let's try to understand how this C1 is generated. Now C1, obviously it is the carry that is coming from this full adder, where I'm adding A1 to B1 and the output is sum 1 and the carry is C1. So C1, we're gonna say that I will have a carry here in one of the two conditions. Either I generate the carry in this bit position 1. How? Well, this is when both A1 and B1 are 1s. If A1 is 1 and B1 equals 1, then I will definitely generate the carry. Well, suppose this is not the case. Well, or the other case is that I have a 1 coming at the Cn, okay? So I have a 1 here coming at the Cn, and then I'm able to propagate it. And what condition would be? This is when Cn equals 1 and one of the A or the B is 1s. Okay, so P1 means here, P1 means what? It means A1 exclusive or B1. In that condition, I can take the Cn or C0, it's the same thing, by the Cn or C0, and propagate it to C1. So again, what are the conditions to generate C1? Either I generate it at bit position 1, or I have a previous, the carry n is 1, and I can propagate it through the first bit to the second bit. Okay, and an obvious example here it will be is that if I have carry n of a 1 and one of the A is 1 and B is 0, now I propagate Cn all the way to Cn all the way to C1. Now let's see how I can generate C2. Well, C2 is generated by a group generate from bit 0 all the way to bit 2. And this happens by either one of the two conditions. Either I generate the carry at bit 2, which is right here. I generate at bit 2. Okay, I generate the carry, and this happens when A1 and B1 both 1s. Or I have C1 coming to me as 1, and I'm able to propagate it to C2. So C1 as 1 and propagate 2 equals to 1. One of these conditions will create C2. And notice I can now replace C1 expression over here, and I can get this expression, which says I can generate C2, which is a group generate from 2 to 0, if I can generate the carry in this bit. Okay, let's choose another color here. Okay, if I can generate the carry at this bit, or I have generated the carry at this bit, which is bit 1, and I'm able to propagate it during bit 2. Or I have Cn or C0 as 1, and I'm able to propagate it through bit 2 or position 1 and position of bit 2. Okay. Now I can carry on and say, okay, what's generate C3, which is this one here. It is a generation of a group generate from bit position 0 all the way to 3. And this occurs if I generate at bit position 3 the carry, or I have C2 here and I'm able to propagate it to C3, C2, C3. But notice C2, I expressed it here. So I substitute it and I get this expression. Now, this expression, right? This expression says the following, that C3 is generated in one of the following conditions. Let's choose another color here. Okay, so in one of the following conditions. Condition number one, I generated here. Condition number two, I generate the carry in bit 2 and I was able to propagate it. Condition number four, I generated at bit position 1 and I was able to propagate it to C3 by having P3 and P2 are 1s. And then finally I have a 1 at the Cn and I was able to propagate it here by P1 and end it by P2 and end it by P3. Okay, finally, how about C4 here? Okay, and we'll do it with this, okay, C4. So C4 here, which is C out, is equal to the group generate of a carry from 4 to 0, from 4 to 0, right? From 4 to 0. And that, how is this computed? Well, either I can generate at bit position 4, or I have C3 and I can move it to C4 by propagation, C3, and I can propagate it. Now I know that C3, I have computed this, so I plug it in and I get this expression for C4. And it says that C4 is generated by one of the following conditions. Well, first of all, I can generate C4 if I can generate it in this bit position, or I generated at 3 and I propagated at bit 4. So I generated at 3 and I can propagate it at 4. Or I generated at 2 and I propagated it at 4. Or I generated at 1 and I propagated all the way to C4. Or I generated, I have Cn coming here and I can propagate all the way to the end. Okay, so a good example for this case, for instance, if I have, let's say, for example, A equals 1, 1, 1, 1, and B equals 0, 0, 0, 0, right? And Cn as 1, right? And Cn as 1. Watch, this is P, this P1 is 1, P2 is 1, P3 is 1, P. So now you can see I'm going to get 0 and a carry, 0 and a carry, 0 and a carry. I'm propagating all the way until I get a carry out of a 1. So what happened? I propagated the Cn all the way to C out. Okay, and that is this is the case. And you can think of other cases as you desire. Let's say, for example, and let's take an example of this case where G4 equals 1. So an example will be if A, for example, is 1, 0, 0, 0, and B equals 1, 0, 0, 0, and let's have Cn of 0. Now, notice that here I'm going to get 0, 0, 0, oh, until I get here. Watch, I'm going to get a sum of a 0 and a carry out of a 1. This is because the generate 4 here equals 1, because both A and B at the bit position 4 are 1s, and therefore the generate 4 is equal to 1, and therefore I can, this term is 1, making C4 as 1. Okay, this is a mess. This is a big mess, okay? And the reason it is a mess because of the following. Let's go to the whiteboard here. Okay, so let's clarify where is this mess. You see, for 4-bit adder, for 4-bit adder, okay, so this is a 4-bit adder. To generate the C4, I need a I need 5 input OR gate. Okay, the first here is G4, and then an AND gate here with P4 G3. This is C4, and an AND gate here of P4 P3 G2, and an AND gate here of P4, P3, P2, G1, and an AND gate here of P4, P3, P2, P1, and Cn. This, if I have 64-bit adder, it is clear that this hardware will be huge because this hardware grows linearly with what? With the size of the data. So you will have to have a 65 fan in OR gate, and then you will have to have an AND gate from two inputs all the way to 65. This is huge hardware. So this is no good. This is possible for small adders, but when you talk about 64 and 48 and 128 adders, this becomes huge hardware, and we will have to find another way. And this is going to be the topic of next lecture. Thank you very much.